and go over a couple of announcements. Okay. On the administrative calendar, there's nothing really new for this week that I think would concern you, so I'll probably trash that one after today's class if I can remember to. And on the volleyball schedule, today's the 28th, so the next thing on the schedule coming up is just Friday, Saturday, and Sunday. I guess it's National Junior College Athletic Association, I'm guessing that's the name, NJCAA, District L/M. I don't know what that stands for. Tournament will be held in Boaz, Alabama. So if you happen to be up there this weekend around Boaz, stop in and cheer our team on to their tournament victory. I don't know if this is the end of the season or just the end of the fall season. I don't know when volleyball season is, if this has been it or if this is just preliminary. I don't know that kind of stuff. And then, this one I've read to you before. This is from a Dr. Christina N. Mora. She's one of the newest cohorts of merit scholars at UAB. I don't know what those are. Sounds good, though. She came across this 1-week summer opportunity for college students interested in biopharma manufacturing careers. Biopharma, I take it, is the biological end of producing pharmaceutical drugs, okay? Biopharma manufacturing careers. I thought one of your students might be interested in applying. The students are paid $1,000 for this 1-week summer opportunity. They're paid $1,000 and travel expenses are covered, okay? So wherever they take you to for that week, they're paid to get you there and get you back. The application deadline is sometime in January, and that's all I know about it, but there are links here that you can go to and find out more information. I can't decipher what the link stands for. It's niimbl.force.com, and I'm assuming that's National Institute for who knows what all. And something another biological labs, I don't know. But anyway, sounds like a great opportunity. If you're interested, please get the information from here and apply. All right, well, I guess we'll get started based on what we know. We're in Chapter A, Integration Techniques and Improper Integrals. 8.6 is numerical integration, and we had talked about the trapezoid rule. Now, they mentioned here that we had done midpoint rule back in section 4.2, which would have been back in Cal 1. I guess I remember it, but not that well. And how you approximate the area under a curve is what they were doing back then. So here are the two approximations, formulas that you have for these two rules. First, the midpoint rule. Let me get my pen set up. Okay, the midpoint rule. Okay, if you have an integral going from a to b of some function f of x dx. Now, the examples that we've had so far have been example 1 was one you know the answer to, okay? But let's assume it's one you can't integrate. This is where it's more useful. Here's what the approximation is by your numerical integration. For the midpoint rule, it would be the summation from I is equal to 1 to n. Okay? All right. Now, your F that you put here is the average of the left endpoint and your right endpoint. So that's why they call it the midpoint rule. It's x sub I minus 1 minus, plus, okay, because it's the average, plus x of I over 2, okay, times delta x, okay? All right. And the trapezoid rule, all right. Fred is here. I have a grandnephew named Brooks, so I'm going to be likely to call you Brooks. But no, his last name's Frederick. No, I'm just kidding. It's not that bad. It's Fowler also. The trapezoid, but his middle name is Charles, so he's almost by namesake, but not quite. The trapezoidal rule. Now these almost look similar, but they're definitely not. A to B of f of x dx, so you're approximating the same function here, and the summation starts the same. I is equal to 1 to n. Now, in this case, it's your f of x sub I minus 1 plus f of x sub I over 2. You're averaging the y values, so to speak, times your delta x. Okay? They sort of look similar, but they are definitely somewhat different. Okay? Now, trapezoid rule is fairly easy to calculate, again, so to speak, because all you're doing is you split your interval into n subintervals, just like we have done before, and then you evaluate this one once, and that's over 2. You'll do this one as the average of the first one, but then when n goes, this is at 1, then when n goes to 2, or I goes to 2, then this becomes f of x sub 1. Okay, so here you have f of x sub 1 when I is equal to 1. Here, this is f of x sub 1 when I is equal to 2. So basically you have that one twice, so the first one, x of I, or x of 0 actually that would be, and that by the way is always your A, that would be 1 time, so it's 1/2 of that times your delta x, and then each of the others, because they show up twice, this over 2 plus this over 2 again would just give you that, so f of 1 plus f of 2 plus f of 3 plus f of 4, all the way up to f of n minus 1 would just be counted once, and then f of n, the last one, is back over 1/2 again. And that's what we did in the trapezoid rule. So basically what you have there is your function, your curve, and you're doing the border points of each of these intervals. Okay? You got f of A, the first one, and then f sub 1, 2, 3, and you're doing the values there, and that's what you're summing. Half of this one, half of the last one, and 1 everywhere in between. Now, how's the midpoint rule different? Okay. This one, you take the midpoint of your x's. Okay. So the first one would be x of 0 plus x of 1. So this would be like x sub 1/2. Okay. And that's what you calculate your f out, that point. And you multiply that by your delta x. So in effect, what you're doing, I'm just going to draw some random curve here. I'm going to take this we keep getting students. That's good. Dawson's here. Okay, top part of the alphabet is doing pretty well, 3 out of 4. The bottom part of the alphabet, 0 out of 5. Okay, so top alphabeters, way to go. So, if this is your function, okay, and this is your interval, say A to B here, I'm going to take the point here and have this be this would be x sub I minus 1, and this is x sub I, okay? What you would do with the midpoint rule, you take the midpoint between these two, and this would be your approximation, okay? The value at the midpoint. Whereas the trapezoid rule takes the value there and averages the value, okay? Actually, the midpoint rule is a little more precise. You can see this on a place of large curvature, that the midpoint rule does come out a little bit better. Trapezoid rule, I've exaggerated it here. That should be a lot closer. They're close. They're very close. But here in the trapezoid rule, you're taking the average of the function value, and the midpoint rule, you're taking the function at the midpoint between the two extremes. Okay? So those are the difference in those two rules. They come out fairly close to each other in the sense of error. Midpoint rule is actually a little bit, in general, lower error than the trapezoid rule. But here's the other thing to note. The trapezoid rule underestimates here, the midpoint rule overestimates here. So, by sort of combining both of them together, you then get a better approximation. And without realizing it, maybe, that's exactly what Simpson's rule does. Okay. My goodness. You steal my heart, dude. Ryan's here. Okay.
Rather early.
Huh?
Rather early.
Yeah, from a relative sense, yes. Okay. All right. So we've got 4 out of 4 of the top part of the alphabet and 0 out of 5 of the bottom part of the alphabet. Not good. Okay. And in a sense, Simpson's rule combines them both. Now, it's not obvious that's what Simpson's rule is doing, but in effect, that's what it is. So let's take a look and see what to do. One way to view the trapezoid approximation of a definite integral is to say that on each subinterval, you approximate f by the first degree polynomial, and in Simpson's rule, named after the English mathematician Thomas Simpson, a potential paper topic there, you take the procedure one step further and approximate f by a second degree polynomial. In other words, you take this point, that point, and the midpoint, and you do the closest parabola you can that fits those 3 points. It's sort of curve fitting for a parabola, okay? Which now you can kind of see how that combines midpoint and trapezoid rule together. So here is a theorem. Oh, I'm sorry. I wouldn't have read all that if I'd known that was on this. Well, I would have read it, but okay. One way to view trapezoid approximation. So just to say, definite integral is to say that on each subinterval you approximate f by a first degree polynomial. the straight line between those two things. That's a linear approximation. You approximate f by first degree polynomial. In census rule, you take the procedure one step further, approximate f by second degree polynomial, endpoint, midpoint, okay? And do the closest parabola you can get between those. Before presenting that, consider the following theorem for evaluating integrals of polynomials degree 2 or less, which would be degree 1 or 0. So here's the integral of a polynomial, p of x, in the form of ax squared plus bx plus c. If this p of x is equal to ax plus b, ax squared plus bx plus c, then the integral here, okay, of that would be, this is just a theorem here, b minus a, that's the length of the interval that you're integrating over, divided by 6, okay? Trying to remember what our other one was. I believe it was 2 if it was anything. Let me see. It was 2n is what we divided that by. But this is just a single polynomial, okay? So hang on to that concept. Then you'll evaluate it at the first point, and then at the last point, okay? And in between, you do the average point, that's that midpoint rule, right? B plus A divided by 2, but give this a weight of 4 times the polynomial evaluated there, okay? This is the polynomial evaluated at the endpoint, polynomial evaluated at that endpoint, and then give 4 times the weight to the polynomial evaluated at the midpoint. This is just a theorem that says this is how you estimate the area under a second degree polynomial, okay? All that's preceded by b minus a over 6, okay? Just out of the blue, this is a theorem, okay? Now, for those who are interested in proving theorems, it actually is not a bad one to do, because I don't think they show it here, do they? No. So let's do this. This is your p of x here, so this would be the integral from a to b of ax squared plus bx plus c dx. Just putting in this p of x where they say p of x down here, okay? We can do that, right? That's not that bad to do. Take the, of course we don't know what a, b, and c is, but with that in mind, what would be the antiderivative of ax squared? Help me somebody. Ax cubed over 3 bx squared over 2 cx, okay? Now, and you would evaluate this from a to b. This is a definite integral, okay? Now, that takes a little bit of stuff to do, but it's not awful. Let's do each term from a to b, not do all from b and then all from a. Let's just do from a to b for each term, just as if we had 3 little integrals here, okay? If you had done that, you know, then this would be a over 3, right, times b cubed minus a cubed, right? Just plugging in that value for x. Plus b over 2 times x from b squared minus a squared, okay? Plus c times b minus a, okay? Now, I don't have a lot of room left here to do anything on. Each of these terms has a b minus a in it, right? And they also have fractional forms. So the least common denominator of fractions is 6. So let's pull out the b minus a over 6. Hey, that's pretty convenient, isn't it? Okay, what do we have left? Okay, we have a 2a on this part times b squared minus, okay. I did it, but I didn't explain it. Sorry. Do you remember how you can factor the difference of two perfect cubes? B minus a times b squared plus ab plus a squared. Did y'all remember that one? The product of two different perfect cubes can be factored that way. This one, of course, is b minus a times b plus a, and of course that one's just b minus a. Sorry, I forgot to throw in that a little bit. So you got a 2a here times b squared plus ab plus a squared plus 3b, because you had a 6 in this denominator, you're going to need a 3 up there, times b plus a plus 6c. Okay. I'm sort of wishing I hadn't done this, but anyway, it's in process now. There's your b minus a over 6 on the outside, 2a times your, and they rearranged to a squared plus ab plus b squared, that's fine, plus 3b times b plus a. Why didn't they rearrange that one? I don't know. Plus 6c. Okay. Now, we're not going to mess with this right now. That's off to the side. But let's do this part, the part inside the brackets there. Okay. What we want to do is pull out the closest we can to what we started with. A squared plus bx plus c. Okay? But rather than x, we're going to have a squared. So it's a b minus a over 6 times. Okay. If you do a times that, it really would be 2a times that, but we're just going to do that. That would give you a little a squared, and then this would give you plus b times little a, and then you have just plus c. Okay. Now, what are you missing? I probably shouldn't put them in brackets yet. Put that in parentheses. Okay. All right. All right. Now, what have you left uncovered here? Okay. Now I'm really regretting doing this. You had 2a squared. We pulled one of them out, so you still have an a squared. And you have a plus 2ab plus 2ab squared plus All you pulled out was 1b times a, so you have 2 capital B A. And one thing I have as if this is a plus here, not a times, sorry. Okay. 2BA plus 3B little b plus 5C. All right. That's everything left over from this. Okay? Now, I'm really regretting this totally. Okay? I should have at the same time been pulling out my B terms. And so let me go back and do that. Sorry. Okay. Let me pull out the B terms as well. A. Okay. We go back up here. We had a 3B B. Wait, here. We had a 2AB squared. I'm going to pull out an AB squared. So that'll be an AB squared. Okay. So that left me just one AB squared. Because I had one A squared left, 2A, okay. And one AB squared left. Okay, pulling one of those out. Pulling out a one B plus capital B that left me one of those and one of those. No, two of these. Okay. All right, two of those. And then pulling out a C, it's just like this form here, but with B's in it, that left me with 4 C's. Okay. Now, that's better. Okay. And again, this is a plus in between those two. Boy, am I regretting doing this. Okay. Now, what is that that's in the middle? Okay. They just skip so stinking many steps here. For me to fill in all the gaps, it's just pretty horrendous. But if you look at this and do, notice this is a squared plus 2ab plus b squared. Well, this got it started for you. I'll let you follow through the rest of the book. It's there. It just is not at all what I consider intuitively obvious. Okay? But what this is, the front end here is P of A, and this back end here is P of B. And what turns out in the middle part is exactly this. Okay? And they just do a voila, it's it, without explaining why. Okay? And if you take this term here, now they do A plus B in the book, in the proof, they have B plus A. It doesn't matter, that part. Okay? What they do, they pull out of this to get rid of your it's a pain in the neck how they do it. But I'm sorry I started that. It does work out to be exactly this, okay? Long, involved process. Sorry I started it, but that's what you got. Okay, now, let's move on. To develop Simpson's rule, this is the top of page 562. To develop Simpson's rule for approximating an indefinite integral, you again partition the interval a to b into n subintervals, okay? Each of which has a width delta x equal b minus a over n. That's just like we did for way back in the midpoint rule, just like we did recently in the trapezoid rule. That's how you start. This time, however, n is required to be an even number. That wasn't necessary before, but it's required to be an even number here. And the subintervals are grouped in pairs like this, okay? Your A is your first one, x sub 0, but then you go x0 to x2, not x0 to x1, and do one at a time, you do two at a time. That's why you have to have an even number for n. So this is one grouping, 0 to 2, 2 to 4, 4 to 6, 6 to 8, n minus 2 to n, because n has to be even. That's your last one. And the last one, of course, is your b. On each double subinterval, x sub I minus 2 to x sub I, you can approximate f by a polynomial p of degree less than or equal to 2, which is the thing we were just looking at, okay? So on each subinterval, okay, that you use there, you approximate it with that. You have 3 points to play with now, endpoint, and midpoint, okay? For example, on the subinterval 0 to 2, choose the polynomial of least degree passing through the point x sub 0, y sub 0, x sub 1, y sub 1, and x sub 2, y sub 2. Okay? Well, a straight line, you can't get a straight line to go through those three. So you're going to have to use it says the least degree. Degree 0 is not going to work. Degree 1 is not going to work. But degree 2, yes, you can have one that goes through those 3 points. Now, notice here, this this polynomial overestimates here, underestimates here, and those two come really close to balance each other out. Of course, they don't exactly, but they do come closer than either midpoint rule, which always in a one like this, midpoint rule would have been, I think, an underestimate always, and the trapezoid rule would have been pretty close to an overestimate always. This one balances out, okay? A little bit of problem in that you got a change of direction here, but it worked out. So anyway, this polynomial, which we know exactly, approximate that function value. Not exactly, but it approximates. Okay. Now, using P as an approximation of F on that subinterval, you have that this thing 0 to 2, x of 0 to x of 2, f of x dx, that's your actual function, is approximately the same as the integral from x sub 0 to x of 2 of p of x dx. And what this is, remember, is your endpoint, x2 minus x0, b minus a over 6, times p of x sub 0. The p of x sub 2 is over here, but 4 times p of the midpoint between those two, which is x sub 1. Okay? So you got, all right, they pulled another sort of sneaky one here, but it's okay. It's legal in most states. Okay? This x sub 1 here, that's exactly what x sub 1 is. this is tricky. B minus A over N is your delta X. Remember, that's from earlier, okay? Now, this is two delta X's, right? This is X0 to X2, not X0 to X1. So this is two delta X's here. So that's where this 2 suddenly showed up from. So this is 2 times the distance between these 2 points, between either one of those two, and the distance between either one of those two is B minus A over N. So that's where the 2 showed up here, okay? Over 6, that stayed here. But this is your delta X, which would be the difference either between X of 0 and X of 1 or X of 1 and X of 2. You got 2 of them, so it's 2 times that. And then this part is this. This is your X of 1 and that. Now your approximation is B minus A over 3N, because the N from here, 2 and the 6 go out, 3N times this thing. Okay. Now, this is the thing we should be comparing back to the both the midpoint and trapezoid rule. What we were using as a delta X then was B minus A over N. Now it's a B minus A, it's a third that, okay? And then we got 3 values here. Now if you repeat this on the entire subinterval A to B, the next one would be from X of 2 to X of 4. So you have another X of 2, so you get 2 F of X of 2s, 4 F's of X of 3s, and then 1 F of X of 4. But then when you do 4 to 6, you pick up another X of 4, 4 X of 5, and 1 X of 6. You keep on going until that last one, just like the first one, only has 1, and every other one in between has 2. The even ones have 2, the odd ones have 4. Okay? Now that is a really sloppy way of saying it, but that's what leads to this. Let F be continuous. The F function has to be continuous on that interval A to B, or else these don't make any sense at all. And let N be an even integer. Simpson's rule for approximating the integral from A to B of F of X dx is then this. Interval A to B F of X dx will be approximated as B minus A over 3N. Okay? That's your prefix. That's no longer your delta X, but it's sort of acting like that. And then you take your F of X of 0, which is your A, F of A, once, 4 times your, okay, split your interval into N subdivisions. A being the first, B being the last, and then an even number of N's in between. Okay? So you got 1 F of A plus 4 F of X1, 2 F of X2, 4 F of X3, 2 F of X4. All the even ones are 2, all the odd ones are 4, except the 0 and the last one, which N has to be an even number, is just one of each of those. Okay? And as N approaches infinity, in an even sense, the right-hand side approaches this. And it approaches it pretty quickly. Much more quickly than either the midpoint or the trapezoid rule do. Okay? So let's actually do one. Use Simpson's rule to approximate our favorite one here. 0 to pi of sine of x dx. Because we know what this answer is, don't we? Remember it from last time? Oh, no, that was too many days ago. Anyone remember what that was? Oh, look back in the note. I'll remind you. It was 2. Because it's cosine x, minus cosine x dx, right? And cosine of pi is -1, but it's a minus cosine, so that makes it a 1. Minus a minus, minus a minus, because it's minus cosine. Cosine of 0 was 1, so it's 1 plus 1 equal 2. Okay. Now, we'll estimate this when n equal 4 and 8. Now remember before we did the trapezoid rule for n equal 4 and 8 as well. Okay? And we got 1 point, just to remind you, trapezoid rule of 4 gave this as approximately 1.896. And trapezoid rule of 8 gave us approximately 1.974. Neither one are bad estimations for 2. Of course, a T8 is much better than T4. But let's do S8, or S4 and S8. So S4, okay, the first thing you're going to do is break your interval from 0 to pi. And frankly, I like to do it on a graph. 0 to pi. Okay, that's just approximately the sine curve. Pi halves, pi fourths, and 3/4 pi, just like before. It's supposed to be 3/4 pi. That's ugly. Okay, that's still ugly, but it's not as ugly. Okay. Now, this is only going to take 2 iterations of the trapezoid rule because you do 2 at a time. So what that will be, I'm sorry, not trapezoid rule, Simpson's rule. T4, that's what we've lined it up to be. I can't, it must be Monday. Okay. Let me see if I can get T4 written. There, I got it. Okay, what would that be? Simpson's rule is B minus A, that's pi, divided by 3n. Your n was 4 on this one, right? 3 times 4 is 12. So pi 12ths times, now, we're going to evaluate at each of these points. Okay? It's going to be 1 of f of 0 plus 4 times f at pi fourths plus 2 times f of pi halves plus 4 times f of 3/4 pi plus 1 times f at pi. Okay. Follow? That's exactly what it said here. The b minus a over 3n, 1 f of 0, 4 f of x1, 2 f of x2, 4 f of x3, and then 1 f of b. Okay? Why did it do that? I hit the wrong button, that's why I did it. Okay, so let's see what this is. Pi 12ths times, what's f of 0? Sine of 0. Please tell me. Sine of 0. 0, all right. Given a multiple choice there, okay. Plus, now remember what sine of pi fourths was? Root 2 over 2. 4 times that would be 2 root 2. Right? Got it? No. Okay. Sine, now it doesn't say derivative of anything. Sine of pi fourths. I'm sorry?
I know it now. I'm sorry, I misheard you. That's why I was confused.
I can't hear.
So unit circle sine of pi over 4 tells you that is root 2
over 2. And then you got 4 of them. So this will be, you got 4 of these, so 4 of those, 2 root 2. Right? Okay. Plus, and what's sine of pi halves? 1. So you got 2. 2 times 1. Yeah. 2 times 1 is 2. And then 4 times sine of 3/4 pi. But guess what? 3/4 pi is the same as 1/4 pi. Sine of 3/4 pi is the same as sine of 1/4 pi. So there you have another 2 root 2 plus 0. All right. So this gives us 4 root 2 plus 2 times pi 12ths. So someone with a handy-dandy calculator, do 4 root 2 plus 2. I could almost do that one in my head.
4 root 2 of what?
Say again?
4 root 2 what?
4 root 2 plus 2. And then multiply it by pi, divide by 12. Almost times 1/4, but it's not quite. 2.005. Is that what you said? Look at that, folks. One iteration got you much closer to 2 than T4 did. S4 got you much closer than T4. It got you closer than T8. If this had been on the other side, that would have been a 1.995. We're at 1.974. So, yeah, you're closer than that. Already on 4 divisions. And here's Jemiah. Now the top part of the alphabet's 5 for 5. The bottom part of the alphabet's O for 4. Okay. Still doing well. Okay. Now, let's do it with 8. Okay? Can I go on and erase T4? Oh, this isn't T4. This is S4. Sorry. Who is paying attention? Huh? That's a S4. 2.0. So I'm going to write that at the top. S4 is approximately equal to 2.005. Okay? I'm going to erase most of the rest of this. Okay? And this time, get your calculators ready. Because you're going to need them. I could have left that, but I didn't. Okay. S8 is what we're going to do next. It's going to be B minus A which is pi, divided by 12 again. That part's the same. So pi 12ths, well, I'm going to need more room. Okay, sorry. Yeah, I think I already erased that. So let's start. Yes. Oh, you're right. Yeah. Okay, let me get this in. 3 pi 8ths and 5 pi 8ths and 7 pi 8ths. Okay, yeah, you're right. The n changes over 3n. N is now 8, so that's over 24. You're right. 24. All right. Your alpha 0 is still alpha 0. We know what it is. That's 0. The next one is 4 times. You know what I think I'm going to do there? It's going to take more room to write, but I think it's worth it. Let's erase all that. All right. I was trying to be cheap with my writing. Okay. Sine of 0, we know what that is. Plus 1/4 the sine of pi 8ths. No, I'm sorry, 4 times. Goodness gracious, where's my brain today? 4 times the sine of pi eighths. Okay, plus 2 times, you tell me, the sine of pi fourth. Oh, good catch there. Plus, tell me next. What's your coefficients doing? One's only the first one. Then it's 4, 2, 4, 2, 4, 2, 4, 2, 4, till you get to the end. So this will be another 4 times the sine of 3/8 pi. Next, plus coefficient, 2 times the sine of next interval was pi halves, right? Okay. Plus 4 times the sine of help me somebody. Five pi eighths, okay. Plus, why am I writing backwards? Any ideas? What coefficient? 2 times the sine of 3/4 pi, which is pi fourths, but we're not there yet. Plus, and what's the last one? Sine of, oh, I've left off this one, sorry. 4 times the sine of 7 pi eighths plus pi sine of pi. So you see what we've done here? It's 1 times this one, which is 0, twice times the sine of this one, 4 times the sine of this one, twice the sine of this one, 4 times the whoops. 4 times the sine of this one, twice the sine of this one, 4 times the sine of this one, twice the sine of this one, 4 times the sine of this one, twice the sine of this one, and 1 times the sine of that one, which is 0. Now, the good news is that these two values are the same, these two are the same, these two are the same, and all you've got to do is that. That's why I wrote them this way, so you can do them a little more easily. This will be pi over 24 times, we know the first one's 0 and the last one's 0. So let's just forget about that one. And this will be 8 times the sine of pi eighths. I don't know that one. You're going to have to do that one on your calculator. Plus 4 times the sine of pi fourths, which and 3/4 pi, which is the square root of 2 over 2, right? We knew that one, didn't we? Plus 8 times the sine of, we'll do 3 pi over 8, which is the same as 5 pi over 8, sine of pi 5, the 5 pi over 8, plus, and those is, again, 2. And this, surprisingly, maybe, comes up to be 2 root 2 again, okay? But we got 2 more in there. So you with the calculators, 8 times sine of pi eighths. You don't have to give it to me, you can just do it. Plus 2 root 2, plus 8 times the sine of 3/8 pi, plus 2. Add all those together, multiply by pi, divide by 24. Say again?
Can you say it again?
Okay. 8 times sine of pi eighths plus 2 root 2 plus 8 times the sine of 3/8 pi plus 2. Add those together, multiply by pi, divided by 24.
What's the one before 2?
This one here,
Yeah.
3/8 pi. 8 times the sine of 3/8 pi. You could have done 5/8 pi with the same value.
I got 2.000.
Oh, okay. 2.00 what? 3? Ooh, we only decreased that much. So S of 8 is approximately, huh?
We got an extra 0.
Oh, an extra 0. 0, 0.
Yes,
3
3 zeros.
zeros and a 3. That sounds a lot better. I'd say we're getting pretty close, wouldn't you? T8, we were still more than 200ths off. Now we're within 3 10,000ths, right? That's a lot closer. Okay. Midpoint rule would have been just slightly better than trapezoid rule. Very slightly better. Simpson's rule wipes them out big time. Okay. Because it takes the best of both of them. We're still overestimating a little bit, and that's okay. All right. Let's see what we got here. Yes, 2.005 was our estimate on S equal N equal 4 and 2.0003. Yes.
Is Simpson's rule always going to be more accurate than the other two every time in every situation?
I hate always. I never say never, or never say always, but I think it will. You would have to have a real okay. And it comes to that definition. If you go back to Simpson's rule, they snuck a weasel word in on you, okay? And here's what it was. I'm trying to find their weasel word. Heck, where is it now? I knew I recognized it when I saw them in there. Okay, there it is. Let's go back a slide or two. Or maybe one more. There it is. For example, on the subinterval 0 to x of 0 to x of 2, choose the polynomial of least degree passing through those points. Now, if this had been a straight line or something very, very, very close to being a straight line, you might could have gotten a linear function to go through it. Okay? So you get that's where the giveaway. If you do that, choosing the polynomial of least degree, if you had a straight line function and you use Simpson's rule, a parabola doesn't fit it very well at all. Okay, so that's where this least degree passing through the points. Usually that's going to be a quadratic. However, it may not be. If those 3 points happen to line up linearly, you use a first degree polynomial, which is a straight line. That's a very rare circumstance, incredibly rare circumstance, but you wouldn't use the polynomial, I don't, the quadratic then, okay? But maybe you would. Maybe you still use Simpson's rule, but you just don't do it. It's now not it would be a linear function rather than a quadratic. And I don't know, maybe all the other things would still work out better. But that's the only reason I would even hesitate to say. I'd say otherwise, yes, always, okay, except possibly that one circumstance, okay. Okay, if it's any kind of a curve, yeah, this is going to work better. Okay. Oh, let me erase my stuff so we can see how they did it. Okay, so when n is equal to 4, your integration from 0 to pi of sine x dx, which we know is going to be 2, is approximately b minus a over 3n, so n is equal to 4, this is over 12, sine of 0, 4 times the sine of pi fourths, 2 twice the sine of pi halves, 4 times the sine of 3/4 pi, and sine of pi, which of course is 0. And that gave you 2.005 without showing you any of the work, okay? It was nice of them, wasn't it? Okay. Then when you did n is equal to 8, you have sine from 0 to pi of that. They didn't even line it up for you. They just said this is what it is. But you would do the same thing, except now you'd have your 4 would be sine of 1/8 pi. This would go to a 2 here. That would be a 4 for 3/8 pi, 2 for this one, just like it was here. 4 for 5/6 pi, 5/8 pi, 2 for this one, 4 for 7/8 pi, and then 1 for that one. And that's where you get that. And your b over 2a would be b minus a over 2n would then be pi, b minus a is still pi, divided by 3 times 8 is 24. All right, now here's your error analysis. Oh, 10 o'clock forward. Okay, good.
Sorry, I'm late.
No problem. Oh, okay. I have one tomorrow, so. Well, y'all are coming in almost alphabetically today. Now we're the top 6 out of 6 and 0 out of 3 at the bottom. Okay. All right. Now we do the error analysis, and again, they have a little weasel here that keeps you from saying always. Okay. When you use an approximation technique, it is important to know how accurate you can expect the approximation to be. The following theorem gives formulas for estimating the errors involved with the use of Simpson's rule and the trapezoid rule. And if they are given the midpoint rule, it's going to be awfully close to the same as the trapezoid rule. Not quite, but close. Okay, if f is a continuous second derivative, that's a new requirement here. Before we just said f had to be continuous, okay? Now it has to have a continuous second derivative on AB. Then the error in approximating the integral from a to b of f of x dx using the trapezoid rule is the maximum value of the absolute value of the error will be less than or equal to. Okay? Now notice this may overshoot it big time, but you guarantee it's within this. Okay, b minus a cubed over 12n squared. Okay, so though your numerator is bigger here, your denominator is bigger by a pretty large amount, and then it's the maximum value of the absolute value of your second derivative on that interval a to b. You know, it's a finite interval, so the second derivative has to have a max somewhere in there. Moreover, if f has a continuous fourth derivative, not second, fourth derivative on AB, then the error in approximating this by the Simpson's rule is less than or equal to b minus a to the fifth power. The longer your interval, you're getting more possible error there, except then you're dividing by 180 times n raised to the fourth power times the maximum of that fourth derivative in the interval hb. Okay. So, you're less than or equal to the maximum, or the absolute value of the error is going to be less than or equal to. It could be 0 here, and it could be something greater than 0 here. That's why I hated to say it's always, because this allows it to be less here than there. It doesn't happen frequently, if at all, but it is allowed. Okay? That's why I hesitated badly to answer your question. In general, when using the approximation, you can think of the error E as being the difference between what your actual value is and the approximation. Theorem 8.6, that's the one we just had up there, states that the errors generated by the trapezoid rule and Simpson's rule have upper bounds depending on the extreme values of your second and fourth derivatives in the interval. Excuse me, I got hiccups. Furthermore, those errors can be made arbitrarily small by increasing the n, providing that f double prime and f, the fourth derivative, are continuous and therefore bounded on A to B. Here is example 3, when we actually do this. Determine the value of n, okay, twisting things around on us here. Determine the value of n such that the trapezoid rule will approximate the value of this integral here, from 0 to 1 of the square root of 1 plus x squared dx, with an error that is less than or equal to 0.01. So what n would we need? Okay, what are we going to have to do? Now it's trapezoid rules, so number 1, we go back and find the thing, okay? Your error is less than or equal to b minus a cubed over 12n squared, maximum of your second derivative in that interval. Okay, so what is one of the first? How would you start? Let's write it down. E less than or equal to, what was it? B minus A cubed over, wasn't it, 12n squared, I thought so, times the max of absolute value of f double prime of x in between make sure I said that right, yeah. Because our B here is, our A is 0 and our B is 1. So what's something you got to do? Find what? Okay, that's what we're looking for. You're absolutely right. Well, error, determine the value of n. Yeah, that's what we're looking for. But what are we going to need to know to get that value of n? Second derivative. Yes, do it. So here's our function, f of x. I don't want to write it that way. How do you think I want to write it? Tell me. 1 plus x squared to the negative 1/2. Where did you get the negative? You're going on and taking a derivative, aren't you? It's to the 1/2, right? Square root is just to the positive 1/2. 1 over the square root would be negative 1/2. Right? All right. So let's go to town with this. What would you do first? It's usually where Dawson pops in. Well, okay, we are going to do that. Take a derivative. Take the first derivative. F prime of x is equal to, and you will use the chain rule, but before you do that, how would you begin? Or however you do it, how would you take that derivative?
It would be x times.
Yeah, you're doing well. Skipping a couple steps. X times what? I missed some of that. I was talking. Say it.
X times 1 plus x squared to the negative 1/2.
You got it. Okay, notice he did two things at once. He did the 1/2 of this to the minus 1/2, but then he had a 2x from the chain rule, so the 1/2 and the 2 cancel out. So that's very nicely done. What's next? Second derivative. And what would that be?
You have to do the product rule.
You can either do product rule or quotient rule. I like product rule, so I'm all in favor. What would that be? X times negative x
1 plus x squared to the
negative 3/2. That's well done. Plus. Whoa, where'd you get the 1/2?
Because the derivative of x is 1.
Yeah.
So it cancels out. So you just do 1 plus x squared.
That's it. Just like that, right? Now, that's a bit messy looking though, isn't it? So let's see if we can clean that up a little bit. I want to lead off with the positive, so I'm going to put that first. 1 over the square root of 1 plus x squared. Right? That's the second half of what he said. Minus, now the x squared's up top now, over 1 plus x squared. I regret that I put, okay, I'm going to put the 3/2 here. I'm going to go back and change that to the 1/2 down here. Does everybody buy what I just did? No. I wrote this one first, wrote it like this. And then this one, the minus sign, that's why I wrote it second. X times x, those are numerator quantities. Okay, so they're up there over this thing to the 3/2. Right? Agreed? Not really. Check my math, always. If it's suspicious, let me know. Okay? All right. Been scrutinized. Okay. Now, how do those denominators differ? This one's to the 1/2. This one's to the 3/2. What's the least common denominator? That to the 3/2. Okay. And how do they differ? By what factor? let me put it this way. This would be 1 plus x squared to the 2 halves times 1 plus x squared to the 1 half. Would you buy that? Okay. This denominator here is that one, right? So what would I have to multiply this one by to make it the same as that one? Which is multiplied by 1 plus x squared. Isn't that it? Yay or nay? Multiply this denominator by this. You have to multiply the numerator by that. But this thing is that. Right? Now you have them both to the same denominator. Okay, what do you notice happens in the numerator when you subtract those two? Yeah, the plus x squared minus x squared, they go away, so you have 1 plus x squared to the 3 halves power. Okay, that is your second derivative of that expression, of that function. Now, we want the maximum second derivative when you're going between 0 and 1. Let's pick the endpoints first. What would be derivative of that? What would be the value of that at 0? When x equals 0. Just 1. So f double prime of 0 is equal to 1. F double prime of 1, what would that be equal to?
Also 1.
Really?
No. 2 to the 3 halves.
Second, 2 to the 3 halves. And let's see, 2 cubed would be 8. So this would be the square root of 8, right? Agreed? Now, which of those is greater? 1 or 1 over the square root of 8? 1, yeah. The other is a fraction. And anything in between there is going to be a fraction between those two, isn't it? Which means the max is going to be this one. All right. All right. Now, your error here is 0.01. So let's go back to our formulas here. This is 0.01 has to be less than or equal to, what's your b minus a? 1, and 1 cubed is 1 over 12 times n squared, right? We're looking for n. And this max here is 1, right? So I didn't bother to write it down. I'll multiply it by that 1 and still get 1. Okay, so what are we going to have to do to figure out what n is? What I want to do is multiply both sides by, I can't write. Okay, it's supposed to be an n. That's supposed to be a time sign. That looks more like a comma. Okay, times n squared, and do this times n squared. Rather than having that, let's go on and divide by 0.01. Divide this by 0.01. So that wipes out your n squareds here, wipes out your 0.01 there. What we wind up with is n squared is less than or equal to is that 1 over 0.12? Please tell me you don't need a calculator.
Yeah, that's right.
Okay, good. All right. And what is 1 divided by 0.12? You need a calculator on this one. Okay.
8 1/3.
Second?
8 1/3.
8 1/3. Okay, 1/3. Okay. Let's write that 8.333333 because I want you to take the square root of it. What do you get?
2.8.
Say that again.
2.89.
So what you reckon your n needs to be? 3, yes. If you make it 3, you're going to be safe because anything greater than that. You don't need much to get a pretty good, and this is a trapezoid rule, so that would be legal. Now, kind of glad we didn't do the Simpsons rule with this, or maybe we're going to do it later. But if we had, remember, Simpsons rule, n always has to be even. So we would have had to bump that up to 4. But it would have been different calculations because it's a different formula for Simpsons rule. The trouble is, oh yeah, they're okay. Choose n equal 3. Okay? So, let me erase what I've scratched here. Anyone need it a little bit longer? Okay. And let's see how they did it. Begin by letting f equal your square root of blah, blah, except I wouldn't have written it that way. And finding the second derivative, f prime was x times, just like you did, 1 plus x squared to the 1/2, minus 1/2, which I bet you Dawson just looked at that and told me, no, I'm just kidding. Okay, and f double prime, after a bit of work, we found out it was indeed that. 1 plus x squared to the minus 3/2. We wrote it 1 over 1 plus x squared to the 3/2. Okay. Now, the maximum value of that on the interval is when x equals 0, then it's equal 1. Anything greater than 0, x equal anything greater than 0, your value is decreasing. So the max is going to be at the endpoint of 0. So by theorem 8.6, you can write the absolute value of the error, which is what they gave you to begin with, is the b minus a cubed over 12n squared, absolute value of, I wish I hadn't done this. We should have written the maximum of the absolute value. Oh no! If you left the x, you need that, but we've already determined the maximum is going to be at 0, so that's fine there. And this is going to be 1 over 12n squared times 1. Right? And that, since the e is going to be 0.01, I believe it was, what they, goodness gracious. Okay, what they did is, okay, 0.01 is 1 over 100. And then they took this and just flipped it. Okay? So that's how they got that, which is the same way of doing what we did. And it leads to the same result. Approximately 2.89. But who cares on that? We can't have the n of a fractional form. It has to be an integral form. So make sure it's greater than that. And that's going to be 3. So you choose n equal 3 because n must be greater than or equal to 2.89. Then let's apply the trapezoid rule as shown. They didn't say to do that, did it? But they're just going to go and do that. Okay? So we're just going to use 3 intervals from 0 to 1. So each of these will be 1/3. By the way, can you do this one analytically? Help me out here. Yay or nay? Probably going to need a trig substitution, and I think it will work. But let's see what we get this way. Since your n is equal to 3, and the trapezoid rule is b minus a over 2n, that gives you 1/6. B minus a is 1 minus 0 is 1. Okay, all right, so that's up. And then for the first is square root of 1, twice the, what you get when you put a 1/3 in there, because this is 0, 1/3, 2/3, 1, okay? So twice what you get when you put a 1/3 in there, twice what you get when you put a 2/3 in there, and then 1 times what you get when you put a 1 in there. 1 times these, 1 times that, 2 times this, 1 times 3. Trapezoid rule, not Simpson's rule. Simpson's rule, you couldn't use a 3. Okay. So, those of you with handy-dandy calculators, you can figure out what that would be, and they will tell you about 1.154. Okay? Now, that is your value. Your error bar, remember, was 0.01. So that means if you know this is going to be 1.154, that's trapezoid rule, that's your approximation here. You know you're within 0.01 of that, so it could go down as low as 1.144 or up as high as 1.164. Okay. Frankly, to me, that seems like way too many digits to be carrying around for only a precision of 2 digits. So, but it's okay. This is a math book, not a physics or science book. All right. See what you get there? Here, your trapezoid rule would be that, here would be that, here would be that. By the way, those overestimate every time, so I think the actual value would be closer to this one. Well, certainly that's the upper one. Okay. Now, do they actually calculate it? No, they don't. Thank you very much. Okay. I think that is the last slide. Any questions before I move off this one? Everybody got it? Okay. Oh, there it is. So by adding and subtracting the error from the estimate, we anticipate it to be something between 1.144 and 1.164. Okay? And that's pretty precise. Okay. And that was the last slide. Homework exercises here would include any of the odds 3 through 13. They're all at Calc Chat. 3's at Calc View. Excuse me. Any of the odds between 15 and 23, they're all at Calc Chat. 17's at Calc View. And that first group, you can actually do the actual calculations, I think, of every one of those. That second group, I know that first one, there's no rule I know of that can do that, okay? There are some that will do some of the others, but that first one, And number 21, nah, okay. Don't know about 23, possibly. 24, I doubt it. Now, all that has to be is a continuous function, and I think it is if you define f of 0 to be 1. That will be continuous, okay. Anyway, either 25 or 27, both at Calc Chat. 25's at Calc View, either 29 or 31, both at Calc Chat. 29's at Calc View. 33, do that one, it's a Calc Chat. 36 should be at Calc Chat. Okay? No, I'm sorry, 35 should be at Calc Chat. 37 should be at Calc Chat, and 39 you can explore. Think about doing 39. I don't know if there's an actual answer. It's just sort of thinking through it. Then you can choose your choice of the odds 41 through 45. They should all be at Calc Chat. 47 is a proof, so if you choose to do that, it should be at Calc Chat as well. Okay. Now, moving on from here. Any questions on 8.6 before we leave it? Okay. Say again? 7 minutes, right. Thanks. So let's at least get started in 8.7 for 7 minutes worth. Since I've already done the homework assignment, though, it won't take time doing that. And let's go from current slide. Okay. Still in Chapter 8, Integration Techniques. So far, that's what we're dealing with, not improper integrals. Now, up through 8.6, we were saying, here are all these techniques you can do. And 8.6 said, and here are the ones you can't do a numerical integration. Now, it seems like to me 8.7 should have come in between those two. You know, after 8.6 and before, after 8.5, but before what we did. I would have put these in reverse order, because what 8.7 is doing is integration by tables and other integration techniques. So why didn't you place all the integration techniques together before you got into the numerical? Maybe they just count numerical as another technique. I don't know. But anyway, here we'll find the indefinite integrals using a table of integrals, find indefinite integrals using reduction formulas, which sometimes you can find in tables of integrals, and find an indefinite integral involving rational functions of sine and cosine. So let's start by integration by tables, okay? Not chairs, but tables, okay? Many people find tables of integrals to be a valuable supplement to the integration techniques discussed in this chapter. Another way of saying it, they use them instead of that, okay? But we'll leave that alone. Tables of common integrals can be found in Appendix B, and that's where we'll be heading very soon. Integration by tables is not a cure-all for all the difficulties that can accompany integration. Using tables of integrals requires considerable thought, insight, and often substitution and skill, okay, at seeing connections here. Each integration formula in Appendix B can be developed using one of the techniques that we've just used to verify several of the formulas, okay? I'd say, yeah, one or more of the techniques, okay? So these are just doing things you already basically know how to do just about every one of them, but they're so much easier to use the table. So if you go back to your table, and I have a mark in mine, it's in the back of near the back of the book. They don't put the page numbers in any reasonable way. They put all the appendix pages as A's. Okay, so you just go to the back of the book, and there is an Appendix A, which is one single page. That's the title page for the appendices is A1. Appendix A is A2, and then Appendix B starts at A3 and goes for quite a few pages. I think it's the longest of your appendices back here. Well, maybe not. No, the longest are your answers to the odd number exercises, which take but most of the rest of the time. Pages. Let's see if there's not. Yeah, then your index is, I guess, appendix, whatever the next one. It's a weird way of numbering pages. Well, they don't name that as a separate index, but it's, a separate appendix, but it just continues the page number. So we're somewhere in the A5, A3 through A6. Okay? Now, Formula 4, I'm pretty sure will be on A3. Formula 4. Here it is. The integral of u, how are we doing on time? Is it already over? Huh? 2 minutes. Okay. Let's see if we can get this one in. I forgot to even get the watch out of the pocket. Okay. All right. A4 at the back is what they list here. The integral of u over a plus bu squared. And they say that is going to be 1 over b squared plus a over a plus bu plus the log of a plus bu, then plus c. Okay? It can be verified using the method of partial fractions because there you have a over a plus bu plus a over a plus bu squared. That's how you would do it. And that would give it to you. Formula 19, which is on the next page, A4, top of the page, the square root, the integral of the square root of a plus bu over u du. That looks like just a u substitution. No, integration by parts. Okay, sorry, I forgot the u in the denominator. Okay, and that's how you go about doing that. So much easier, just use this formula. Formula 84, which is way over A6. The integral of 1 over 1 plus e to the u du. That's just, looks, such a high number you would think it was pretty hard. No, it's just a substitution, a u substitution. Not a u substitution, some substitution. V substitution, because use your integrand here. So all these did come from techniques we already have, okay, or combinations of these techniques. They also mentioned that the table is set up according to forms involving u to the n. There's only 2 of those, okay, u to the n, anything other than -1, and then u if n is -1. I mean, the integral if u is n is -1. Okay, then a plus bu, when you square cubes raised to the nth power. Now some of those, like number 9, is what we're later going to call regression formula. Okay, it tells you what to do, and then you keep doing it over and over again. 11, 13 are like that as well. Okay, I think maybe not. Okay. Then forms involving quadratics, and they show you those, and forms involving square roots, forms involving a squared plus or minus u squared, those are going to be your trig substitutions, square root of u squared plus or minus a squared, those are going to be trig substitution, a squared minus u squared, square root of that, trig substitution, sines and cosines, 46 to 58, okay, tangents, cotangents, secants and cosecants, 59 to 73, and so on and so forth. So we'll pick up next time. There's something they said bizarre here that I have a mark by, but we'll just have to wait to do that. I guess we'll do it, and we'll begin with example 1. We'll start with example 1 next time. I have a mark by the log rule here, but I don't know what. Yeah, it's going to be a u substitution using the log rule. Okay. All right. Any questions? Let's end this.